Spiral galaxies are among the most visually striking structures in the universe, their graceful arms winding around a luminous core. They are home to billions of stars, vast clouds of gas and dust, and enigmatic dark matter that holds them together. Their swirling forms are not static, they are dynamic, shaped by complex gravitational interactions and the ongoing process of star formation. At the heart of every spiral galaxy lies a dense, spheroidal region filled with older stars. This central bulge often harbors a supermassive black hole, an invisible force governing the motion of nearby matter. Around this bulge stretches a vast, rotating disk where most of the galaxy's young, hot stars reside. The arms of a spiral galaxy are not physical structures but rather patterns created by density waves, regions where interstellar gas is compressed, igniting bursts of star formation. The movement of stars in a spiral galaxy follows intricate patterns. While the inner regions rotate almost as expected from visible mass distribution, the outer regions defy classical physics. Instead of slowing down, they maintain nearly constant speeds, suggesting the presence of an unseen force. This phenomenon was one of the first major clues leading to the discovery of dark matter, an invisible substance that outweighs visible matter by a significant factor. Spiral galaxies do not exist in isolation. They interact with their surroundings, exchanging matter, absorbing smaller galaxies, and even colliding with their counterparts. The Milky Way itself is currently cannibalizing several dwarf galaxies, stripping them of stars and gas. These interactions leave behind stellar streams, ghostly remnants of once independent systems, stretched by gravitational forces. The formation of a spiral galaxy is a delicate interplay of angular momentum and gravitational collapse. In the early universe, primordial clouds of gas condensed under their own gravity, beginning to spin as they contracted. Over time, these rotating disks developed spiral patterns, sculpted by density waves and the inflow of fresh gas from intergalactic space. Some spiral galaxies are pristine and undisturbed, while others bear scars of past encounters, distorted arms, tidal tails, or bursts of intense star formation. Galactic bars, elongated structures of stars cutting through the center, are common features in spirals. These bars act as engines of evolution, funneling gas toward the core and fueling new generations of stars. They also influence the motion of stars across the disk, redistributing angular momentum and altering the overall shape of the galaxy over cosmic time. Beyond their structure and evolution, spiral galaxies play a fundamental role in the grand scheme of the universe. They are the sites where planetary systems form, where elements essential for life are forged in the hearts of dying stars. Their arms are nurseries of new stars, while their halos contain relics of ancient stellar populations that trace back to the earliest epochs of cosmic history. As we look into the night sky, we see only a fraction of the vast universe beyond our own spiral home. Yet, each distant spiral galaxy tells a story, a history shaped by gravity, time, and the unrelenting forces of cosmic evolution. Their elegant arms continue to rotate, a testament to the vast and dynamic nature of the cosmos. The delicate balance that maintains the structure of spiral galaxies is shaped by both visible and invisible forces. Gravity acts as the main architect, binding stars, gas, and dark matter into coherent, rotating systems. Yet, it is the interplay of motion and energy that sustains their spiral arms, preventing them from winding up and disappearing over time. One of the most remarkable processes in spiral galaxies is the formation of stars. Within their arms, Clouds of cold hydrogen gas collapse under their own gravity, triggering the birth of new stars. These regions shine with the intense blue light of young, massive stars that burn hot and bright but live brief lives. Their explosive deaths as supernovae enrich the galaxy with heavy elements, carbon, oxygen, and iron, that later become the building blocks of planets and, ultimately, life itself. The spiral arms themselves are not rigid structures, but rather moving patterns of density waves. Like ripples on the surface of a pond, these waves compress interstellar gas, creating conditions for star formation. As stars are born, they illuminate the arms, making them appear as permanent features, even though individual stars constantly move in and out of them. This phenomenon helps explain why spiral galaxies maintain their distinctive shapes for billions of years. The halo of a spiral galaxy extends far beyond its visible disk. It contains a vast population of old stars, scattered remnants of ancient mergers, and an unseen but dominant component, dark matter. Unlike the bright central regions, this halo is a ghostly domain, where only the gravitational pull of invisible mass reveals its presence. The exact nature of dark matter remains one of the greatest mysteries in modern astrophysics, but its existence is undeniable. It prevents the outer regions of galaxies from flying apart and sculpts the large-scale structure of the cosmos. Despite their ordered appearance, spiral galaxies are not stable over cosmic timescales. They constantly evolve, shaped by interactions with other galaxies. When two spirals pass close to one another, their mutual gravity distorts their arms, triggering waves of star formation. If the encounter is violent enough, it can strip away gas, warp the disk, or even lead to a complete transformation into an elliptical galaxy. The Milky Way itself is destined for such a fate. It is currently on a slow but inevitable collision course with the Andromeda Galaxy, another spiral giant. In about 4.5 billion years, the two galaxies will begin to merge, their structures dissolving in a cosmic dance of destruction and rebirth. Stars will be thrown into new orbits, their once-defined spiral arms vanishing as gravity reshapes the system into a single, massive galaxy. While this might seem catastrophic, the vast distances between individual stars mean that direct collisions will be rare, though the night sky, as seen from any surviving planets, will be transformed into a chaotic swirl of merging galactic light. Some spiral galaxies, instead of merging, gradually fade into quiet states. As they consume their available gas, the birth of new stars slows down. Without fresh material, the galaxy loses its youthful brilliance, leaving behind a population of aging, cooler stars. Over immense timescales, these galaxies may become lenticular or elliptical, their spiral arms erased by the relentless passage of time. Even beyond their visible features, spiral galaxies hold secrets that extend to the very structure of the universe itself. Their rotation, their dark matter halos, their distribution across cosmic time, all of these provide critical clues about the fundamental laws of physics. By studying them, we gain a deeper understanding of the forces that govern not only galaxies but the entire fabric of space and time. Yet, for all that we have learned, spiral galaxies remain an enigma. Their elegance and complexity invite endless questions, pushing the boundaries of our knowledge ever further. Each observation, each new discovery, brings us closer to unraveling the cosmic story they tell, one written in the language of gravity, light, and the silent pull of the unknown. As we peer deeper into the cosmos, we find that spiral galaxies are not just isolated islands of stars but are deeply interconnected within the vast web of the universe. Their existence is shaped by the cosmic environment, from the influence of nearby galaxies to the filaments of dark matter that thread through the void. One of the most intriguing aspects of spiral galaxies is their place in large-scale structures. They are often found in galaxy groups and clusters, where they interact with neighboring galaxies through gravitational forces. In smaller groups, like our local group, spiral galaxies like the Milky Way and Andromeda retain their form, continuing to spin and create new stars. However, in dense galaxy clusters, spirals are much rarer. The hostile environment of a cluster, filled with hot intergalactic gas, strips spiral galaxies of their own gas, halting star formation and transforming them into lenticular or elliptical galaxies. This process, known as ram pressure stripping, erases their once vibrant spiral arms, leaving behind a population of aging stars. Despite these environmental challenges, many spiral galaxies persist for billions of years, maintaining their delicate structure through a balance of forces. Their rotation is governed by the distribution of mass, including the mysterious dark matter halo that surrounds them. This unseen substance extends far beyond the visible stars, influencing their motion and preventing the galaxy from tearing apart. Without dark matter, the outer stars of a spiral galaxy should move more slowly than they do. Instead, they orbit at nearly constant speeds, defying expectations based on luminous matter alone. This discovery remains one of the strongest pieces of evidence for dark matter's existence. Beyond their role as star-forming factories, spiral galaxies serve as cosmic time capsules, preserving clues about the early universe. Some of the oldest stars in the Milky Way, found in globular clusters and the galactic halo, date back to the universe's infancy, over 13 billion years ago. Their chemical compositions reveal the conditions of the young cosmos, long before spiral arms even formed. These ancient stars are relics from a time when the first heavy elements were forged in the fiery deaths of massive stars, seeding the galaxy with the building blocks for future generations of stars and planets. Yet, for all their beauty and complexity, spiral galaxies are not eternal. Over time, their gas supplies diminish, their arms fade, and their rotation slows. Some spirals merge with other galaxies, while others gradually transition into featureless forms. The future of the Milky Way itself is one of transformation. As it collides with Andromeda, the two spirals will become an entirely new entity. Whether this final structure will be a massive elliptical galaxy or something more complex is still unknown, but one thing is certain: spiral galaxies, despite their ephemeral nature, have shaped the evolution of the universe itself. In every direction we look, across billions of light-years, we see spirals stretching their luminous arms through the void, telling the ongoing story of the cosmos. They are engines of creation, birthplaces of stars and planets, and keepers of cosmic history. Their graceful shapes are written into the fabric of time, whispering secrets of gravity, light, and the unseen forces that bind the universe together. Even as they evolve and fade, their influence endures, leaving an imprint on the vast and ever-changing structure of the cosmos. Spiral galaxies, despite their apparent elegance and order, are dynamic, ever-changing systems. Their structure is constantly shaped by internal and external forces, gravitational interactions, star formation, galactic collisions, and the continuous influence of dark matter. While their spiral arms create an illusion of permanence, they are in reality fleeting patterns in the grand timescale of the universe. A crucial factor in the longevity of a spiral galaxy is its supply of cold gas. As long as interstellar gas remains abundant, new stars continue to form, maintaining the bright, glowing arms that define these galaxies. However, gas is not an unlimited resource. Over time, supernova explosions, stellar winds, and active galactic nuclei expel material into intergalactic space, slowly depleting the reserves needed for star formation. Some galaxies acquire fresh gas by accreting material from their surroundings, either from the cosmic web of hydrogen filaments or by consuming smaller galaxies in a process known as galactic cannibalism. Observations of distant galaxies provide insight into the evolution of spiral structures over cosmic time. Billions of years ago, young spiral galaxies appeared more irregular, their arms less defined, their disks turbulent. This suggests that spirals were shaped by mergers and accretions, with their modern, structured forms emerging as they stabilized over time. Today, we observe spiral galaxies in a mature phase, yet their ultimate fate is to transform, either by merging with other galaxies or by exhausting their star-forming potential. One of the most mysterious and influential components of a spiral galaxy is its central supermassive black hole. These colossal objects, millions to billions of times the mass of the Sun, lurk in the galactic core, affecting the movement of stars and gas on vast scales. In some galaxies, black holes become active, feeding on infalling matter and releasing enormous amounts of energy in the form of quasars or active galactic nuclei, AGN. These events can dramatically alter a galaxy's evolution, heating surrounding gas and halting star formation. The interplay between a galaxy's black hole and its stellar population remains one of the most intriguing areas of astrophysical research. Even at their edges, spiral galaxies display unexpected properties. Beyond the bright disk and halo, astronomers have discovered extended ultraviolet and X-ray emissions, hinting at ongoing processes of star formation and interactions with the intergalactic medium. Some spirals have extended gaseous arms that stretch far beyond their visible stars, shaped by past encounters or the inflow of primordial gas. These hidden features challenge our understanding of how galaxies grow and evolve over billions of years. As we study the most distant spiral galaxies, we gain glimpses into the universe's early history. Some of the earliest known spirals, seen billions of light-years away, appear surprisingly well-formed, suggesting that the conditions for their creation were in place earlier than previously thought. This raises questions about the role of dark matter in cosmic structure formation, as the delicate balance of forces needed to shape spirals must have been established much earlier in the universe's evolution. Despite the vast distances that separate them, spiral galaxies are deeply connected. Through gravitational interactions, cosmic flows of gas, and mergers, they shape one another, exchanging material and energy across cosmic scales. Their fates are intertwined, dictated by the unseen forces that govern the expansion of the universe and the slow, inevitable transformation of galaxies over time. And so, the story of spiral galaxies is one of constant motion, evolution, and transformation. They are not static relics but living, breathing entities within the cosmos, spinning, merging, forming stars, and ultimately fading into new forms. Even as individual galaxies disappear, their stars, their elements, and their legacy remain, woven into the ongoing history of the universe itself. Spiral galaxies do not exist in isolation, they are part of a vast and interconnected universe, shaped by cosmic flows, dark matter scaffolding, and gravitational interactions that extend across millions of light-years. Their graceful forms, though seemingly eternal, are fleeting in the grand scale of cosmic time, constantly reshaped by forces both seen and unseen. One of the most striking features of spiral galaxies is the intricate balance between order and chaos. While their arms appear as stable structures, they are in fact regions of continuous change. Stars within these arms are born, live, and die, enriching the interstellar medium with heavier elements that will fuel future generations of stars. Massive stars explode as supernovae, their shock waves triggering new waves of star formation, while lower-mass stars burn slowly, contributing to the long-term stability of the galactic disk. However, the formation and sustainability of spiral galaxies depend on angular momentum conservation. During their initial collapse from vast clouds of gas in the early universe, their rotation played a crucial role in determining their final structure. This rotation prevents them from collapsing directly into a dense spheroid, allowing them to maintain their disk shape. Yet, over billions of years, galactic mergers and interactions can disrupt this delicate equilibrium, transforming once majestic spirals into chaotic, amorphous shapes. Spiral galaxies often serve as cosmic laboratories for understanding some of the most fundamental questions in astrophysics. They provide direct evidence of how stars recycle material, how gas flows through cosmic structures, and how dark matter governs galactic rotation. Through observations of these galaxies, astronomers have uncovered key insights into the nature of gravity, the role of magnetic fields in space, and the mysterious properties of dark energy. The arms of a spiral galaxy are not permanent, nor are they rigid structures moving in unison. Instead, they are created by density wave patterns, similar to traffic jams on a highway, where cars slow down and cluster together but continue moving. These density waves pass through the galaxy's disk, compressing gas and dust, forming clusters of new stars. As these stars age, they drift away from the arms, while the pattern itself remains. Over time, this process ensures that spiral galaxies remain vibrant and active, producing millions of new stars across billions of years. Beyond their glowing disks, spiral galaxies are enveloped by vast, invisible halos of dark matter, which extend far beyond the visible stars. These halos are crucial for the galaxy's survival, preventing it from flying apart under its own rotation. The exact nature of dark matter remains unknown, but its gravitational influence is undeniable. Without it, galaxies would not rotate in the way they do, and the large-scale structure of the universe would look vastly different. Despite their elegant appearance, spiral galaxies are shaped by violent processes. Their structures are often disturbed by tidal forces, gravitational encounters with other galaxies that can warp their disks, stretch their arms, or even create dramatic, star-forming bridges of gas. Some of the most spectacular examples of galactic interactions show spiral galaxies twisting into peculiar shapes, their arms disrupted, their central regions brightened by bursts of new stars. Over time, these interactions may lead to complete mergers, in which two spirals collide and merge into a larger, more amorphous elliptical galaxy. The Milky Way itself is in the midst of such a transformation, slowly consuming smaller satellite galaxies. Streams of stars, remnants of ancient mergers, stretch across the sky, remnants of systems that were once independent but have now become part of our galaxy. This ongoing process of galactic assembly will ultimately reshape the Milky Way, influencing its structure for billions of years to come. But the most dramatic event in our galaxy's future will be its collision with Andromeda. Over the next few billion years, the two spirals will be drawn together by gravity, beginning a long and complex interaction. Initially, their spiral arms will be torn apart, their gas clouds compressed, triggering massive waves of star formation. Over time, as their nuclei merge, the galaxies will settle into a new form, most likely an elliptical galaxy, stripped of the delicate spiral structure that once defined them. Even as spiral galaxies evolve, their contributions to the cosmos remain eternal. The stars they form, the elements they create, and the planetary systems they host will continue to exist long after the galaxies themselves have faded. The heavy elements forged in their cores, carbon, oxygen, iron, will drift into interstellar space, seeding new generations of stars and potentially new forms of life. In the grand scale of the universe, spiral galaxies are transient structures, yet their influence spans across cosmic time. They are the architects of stellar evolution, the cradles of planetary systems, and the key to unlocking the deepest mysteries of the cosmos. Even as they fade, merge, or transform, their legacy endures, written in the very fabric of the universe itself. As spiral galaxies continue their cosmic dance, their evolution is not just a story of stars and gravity but also of the fundamental forces shaping the universe itself. These galaxies, with their intricate structures and delicate balance, offer a window into the nature of dark matter, the formation of galaxies, and the fate of cosmic structures over billions of years. One of the most remarkable aspects of spiral galaxies is their ability to recycle matter. Every star that is born, lives, and dies contributes to this cycle. When massive stars explode as supernovae, they expel heavy elements into space, enriching the interstellar medium with carbon, oxygen, silicon, and iron, the very building blocks of planets and life. Over time, these elements become part of new stars, planetary systems, and even the atmospheres of habitable worlds. In this sense, spiral galaxies are not just factories of stars but also cradles of chemical evolution, shaping the materials that make up everything we know. But even as spiral galaxies create new stars, they also lose mass to the vast emptiness of space. Galactic winds, driven by supernova explosions and energetic radiation from young stars, can blow gas out of the disk, preventing it from forming new generations of stars. In some cases, interactions with other galaxies strip away gas and stars, creating tidal streams, long, ghostly trails of material stretching across intergalactic space. These stellar remnants serve as cosmic fossils, preserving the history of past mergers and interactions. Despite these continuous changes, spiral galaxies are resilient, maintaining their structure for billions of years. This stability is largely due to the hidden mass of dark matter, which provides the gravitational glue needed to keep their disks intact. While dark matter itself remains one of the greatest mysteries in modern physics, its influence on spiral galaxies is undeniable. Without it, galaxies would fly apart under their own rotation, their stars drifting into the void. Instead, they hold together, spinning gracefully, sustained by the invisible forces that govern the cosmos. At the same time, spiral galaxies are not static objects. Their structures can be altered by internal processes, such as the formation of bars, elongated regions of stars that stretch from the galactic core outward, influencing the motion of gas and stars. Bars act as engines of evolution, driving gas toward the center and fueling bursts of star formation. Over time, they can shape the overall appearance of the galaxy, altering its spiral pattern or even leading to the formation of a bulge in the core. In some cases, bars and spiral arms help direct gas into the central supermassive black hole, triggering periods of intense activity. When enough material falls into the black hole, it can unleash enormous amounts of energy, creating quasars and active galactic nuclei, AGN. These brilliant beacons, visible across vast cosmic distances, represent some of the most extreme environments in the universe. Although the Milky Way's central black hole, Sagittarius A*, is relatively quiet, there is evidence that it has experienced past eruptions of activity, shaping the galaxy's core over time. Beyond their own evolution, spiral galaxies play a crucial role in shaping the cosmic landscape. As they move through intergalactic space, they interact with other galaxies, exchanging material, merging, and even triggering the birth of new star systems. Some spirals are surrounded by satellite galaxies, small companions that orbit their larger hosts. Over time, these satellites are often absorbed, their stars and gas becoming part of the main galaxy. The Milky Way, for example, is in the process of consuming the Sagittarius dwarf galaxy, a small stellar system being torn apart by the Milky Way's gravitational pull. Yet even the largest spiral galaxies are not immune to their ultimate fate. As the universe continues to expand, galaxy collisions and mergers become more common. Over billions of years, many spirals will merge into larger, more featureless elliptical galaxies, losing their arms as their gas is used up or expelled. The Milky Way and Andromeda, currently separated by 2.5 million light-years, are on a collision course that will reshape both galaxies into a new, larger system, likely an elliptical galaxy with little ongoing star formation. Despite this long-term transformation, the legacy of spiral galaxies will endure. The stars they have formed, the planets they have nurtured, and the elements they have forged will persist, carried forward into new structures and future cosmic generations. The galaxies themselves may fade or change, but their impact will remain imprinted in the very fabric of the universe. In every distant spiral galaxy, we see a reflection of our own cosmic home. The same forces that shaped the Milky Way are at work across billions of light-years, weaving the intricate patterns of galactic evolution. Even as the universe continues its inexorable expansion, the spiral galaxies that dot the cosmic landscape will continue to tell the story of creation, motion, and transformation, one written in the stars themselves. Spiral galaxies, though bound by gravity and the unseen influence of dark matter, are not isolated entities, they are woven into the vast cosmic web, a structure spanning the observable universe. This web, composed of filaments of dark matter and gas, serves as the scaffolding upon which galaxies form, evolve, and interact. Within this interconnected network, spiral galaxies exchange matter, merge with smaller companions, and shape the very fabric of space over billions of years. The formation of spiral galaxies is a process still under active investigation, with modern simulations revealing the complex interplay of forces that give rise to their striking structures. In the early universe, vast clouds of primordial hydrogen and helium collapsed under their own gravity, beginning to spin as they drew in material. The conservation of angular momentum prevented them from collapsing directly into spherical objects, allowing thin, rotating disks to form. Within these disks, density waves sculpted the first spiral arms, while supernova explosions, gas accretion, and stellar winds continually reshaped their structure. The spiral arms themselves are transient features, constantly forming, stretching, and dispersing. They are not solid structures, but rather regions of enhanced density that trigger bursts of star formation. These arms appear luminous because of their hot, young stars, short-lived giants that burn bright before ending their lives in spectacular supernovae. Over time, as these stars explode or evolve into dimmer remnants, the arms shift, giving the illusion of a constant, stable spiral pattern. In reality, the material within the galaxy is always in motion, cycling between phases of gas, stars, and interstellar dust. One of the key factors influencing the structure of a spiral galaxy is its rotation curve, the way in which different regions of the galaxy orbit around its center. Unlike in planetary systems, where outer planets move more slowly than inner ones, the outer regions of spiral galaxies rotate at nearly constant speeds. This discovery, first noted in observations of the Milky Way and nearby galaxies, was one of the earliest pieces of evidence for the existence of dark matter. Without an unseen mass component exerting gravitational influence, the outer stars should move much more slowly than they do. Instead, they continue their motion, bound by the enigmatic force of an invisible halo of dark matter. As spiral galaxies interact with their cosmic environment, they experience both growth and transformation. Many spirals accrete gas from the intergalactic medium, fueling new star formation and maintaining their brilliant arms. Others, especially those in dense galaxy clusters, undergo a very different fate: ram pressure stripping. In these crowded environments, galaxies move through hot, ionized gas, which exerts pressure on them, stripping away their cold star-forming material. This process can rapidly quench star formation, leaving behind a gas-poor system that slowly fades into an elliptical or lenticular shape. Even within their own structures, spiral galaxies exhibit subtle yet profound processes of evolution. The central bulge, often dominated by older, redder stars, provides clues about a galaxy's past. Some spirals have small, compact bulges, suggesting a more quiescent history, while others feature massive, classical bulges, which may have formed through early mergers and violent starburst activity. At the same time, galactic bars, present in many spirals, act as mechanisms for redistributing mass and angular momentum, driving gas toward the core and fueling bursts of star formation. Spiral galaxies also play a key role in the grand cycle of galactic mergers, where cosmic structures grow and change over billions of years. Smaller galaxies are frequently absorbed into larger ones, contributing their stars and gas to the larger system. The Milky Way, for instance, is currently consuming the Sagittarius dwarf galaxy, its gravitational forces stretching and tearing apart the smaller system. Over time, these mergers reshape the overall structure of the galaxy, leaving behind stellar streams, elongated remnants of once independent galaxies. On larger scales, spiral galaxies themselves will eventually merge with each other, leading to even more dramatic transformations. The upcoming collision between the Milky Way and Andromeda, set to occur in about 4.5 billion years, will be one of the most significant events in our galaxy's future. As these two massive spirals draw closer, their gravitational forces will distort their structures, triggering immense waves of star formation, warping their disks, and possibly fueling the central black holes of both galaxies. In the end, after several billion years of interactions, they will likely settle into a single, massive elliptical galaxy, devoid of the spiral arms that once defined them. Yet, even after such dramatic transformations, the stellar populations and chemical elements forged within these galaxies will continue to shape the cosmos. The heavy elements produced in their cores will be dispersed into space, enriching future generations of stars and planetary systems. In this way, spiral galaxies are not just transient structures, but active participants in the ongoing chemical evolution of the universe. As we observe the night sky, the spirals we see are not just points of light in the darkness, they are vast, evolving worlds, each telling a story billions of years in the making. Their delicate balance of motion, gravity, and matter reveals the intricate mechanisms governing the cosmos. And though their lifetimes may span billions of years, they, too, will eventually fade, merge, or transform, continuing the endless cycle of cosmic evolution that has shaped the universe since its beginning. Spiral galaxies, though appearing stable over human timescales, are in constant flux, shaped by gravitational interactions, internal star formation cycles, and the vast cosmic forces that govern the universe. Their evolution is an ongoing process, from their birth in the early universe to their eventual transformation into new forms. The formation of spiral galaxies is intricately tied to the primordial conditions of the universe. In the aftermath of the Big Bang, the first structures to form were protogalactic clouds, vast, rotating regions of hydrogen and helium. As these clouds collapsed under gravity, they began to spin, creating the rotational motion necessary for disk formation. The degree of this initial angular momentum determined whether a galaxy would form into a spiral, elliptical, or irregular shape. Early in their history, these galaxies were highly turbulent, dominated by chaotic motions, frequent mergers, and intense star formation. Over billions of years, their structures gradually settled into the familiar disk and bulge configuration, with their spiral arms forming through the action of density waves and differential rotation. Some galaxies developed bars, elongated features of stars stretching across their central region, which helped channel gas into the core, fueling bursts of star formation and feeding the supermassive black holes that lurk at their centers. One of the most enigmatic aspects of spiral galaxies is their unexpected rotational behavior. In a system governed solely by visible matter, we would expect stars at the outer edges to orbit more slowly than those near the center, much like planets in our solar system. However, observations reveal that stars in the outer regions of spiral galaxies move at nearly the same speeds as those in the inner regions, a discovery that led to one of the most important revelations in astrophysics, the existence of dark matter. Dark matter, though invisible, is believed to form a massive halo around spiral galaxies, exerting the gravitational influence needed to maintain their structure. Without this unseen component, the centrifugal forces of rotation would tear galaxies apart. The true nature of dark matter remains a mystery, but its presence is critical for understanding not just the evolution of spiral galaxies, but also the large-scale structure of the cosmos. Spiral galaxies are not static entities, but living, evolving systems that consume and recycle matter. Their spiral arms serve as stellar nurseries, where dense clouds of interstellar gas collapse to form new stars. These newborn stars illuminate the arms, while massive stars quickly burn out and explode as supernovae, enriching the surrounding medium with heavier elements. This feedback cycle, the continual birth, death, and recycling of stars, shapes the chemical evolution of the galaxy and dictates its long-term stability. Yet, galaxies also lose material over time. Some of their gas is blown away by stellar winds and supernova explosions, while interactions with other galaxies can strip them of their cold gas reservoirs, effectively shutting down star formation. Galaxies in dense environments, such as galaxy clusters, often experience this phenomenon, leading them to transition into gas-poor, elliptical shapes. No spiral galaxy exists in perfect isolation. Over time, interactions with other galaxies reshape their structure. Minor mergers, where a spiral galaxy absorbs a smaller dwarf galaxy, can trigger localized bursts of star formation but often leave the spiral pattern intact. However, major mergers, such as the upcoming collision between the Milky Way and Andromeda, result in dramatic transformations. When two spiral galaxies merge, their delicate structures become distorted, triggering intense bursts of star formation as their gas clouds collide. Over time, their arms dissolve, and their stars settle into a new, elliptical configuration. The supermassive black holes at their centers are drawn together by gravity, eventually merging into a single, even more massive black hole. These events are among the most powerful in the universe, shaping the long-term fate of galaxies. Even after merging, a galaxy's stars and remnants do not disappear. The elements forged within its stars are scattered throughout the cosmos, contributing to the next generation of galaxies, stars, and planetary systems. In this way, the material from ancient spirals continues to shape the evolution of the universe long after their original structures have vanished. Because light from distant galaxies takes time to reach us, looking deeper into space allows us to see younger versions of spiral galaxies, frozen in earlier stages of their evolution. The most distant spiral galaxies observed by telescopes like Hubble and JWST appear more chaotic and clumpy than modern spirals, suggesting that the spiral structure itself is a relatively recent phenomenon in cosmic history. By studying galaxies at different distances, astronomers can piece together the story of how spirals formed, evolved, and will eventually fade. Observations show that spiral galaxies were far more common in the past than they are today, meaning that many of them have already undergone transformations into ellipticals through mergers and gas depletion. The long-term future of spiral galaxies depends on the expansion of the universe, dark energy, and cosmic structure formation. If the universe continues to expand at an accelerating rate, isolated spiral galaxies may continue to exist for trillions of years, gradually exhausting their gas supplies and evolving into dim, red remnants filled with aging stars. However, for galaxies that remain in clusters or near neighbors, the process of galactic merging will continue, gradually converting most spirals into ellipticals over vast timescales. In the distant future, the universe may contain far fewer spirals than it does today, with their signature arms erased by the gravitational interactions that dominate cosmic evolution. Despite their eventual transformation, spiral galaxies will leave behind an enduring legacy. The stars they have formed, the elements they have produced, and the planetary systems they have nurtured will continue to shape the fabric of the cosmos long after their spiral patterns have faded. Even in the most distant future, the echoes of spiral galaxies will persist, written into the very structure of the universe itself. As we continue to study spiral galaxies, each new discovery deepens our understanding of their role in shaping the cosmos. From the forces that maintain their elegant structures to the vast, unseen dark matter halos that hold them together, they remain one of the greatest sources of insight into the mysteries of the universe. And as our technology improves, revealing more details than ever before, the story of spiral galaxies is still far from over. It is a story that continues to unfold, written in the stars across billions of light years. Spiral galaxies, ever-changing and evolving, are shaped by forces both internal and external, visible and invisible. Their delicate arms, filled with young, hot stars, illuminate the vast disks that spin through the cosmos, held together by the unseen pull of dark matter. Yet, these spirals are not frozen in time, they move, collide, and transform, playing their part in the grand cycle of galactic evolution. The arms of a spiral galaxy are regions of continuous activity, where dense clouds of gas collapse to form new stars. These regions shine brilliantly in the blue and ultraviolet light of massive, short-lived stars, while older stars drift outward, enriching the interstellar medium with heavy elements. The bright, star-forming arms contrast against the darker, dust-laden regions that weave through the galactic disk, absorbing and scattering light, shaping the appearance of the galaxy itself. At the core of most spirals lies a bulge of ancient stars, orbiting in complex patterns. In the very heart of this bulge, hidden from direct view by dense clouds of gas and dust, lurks a supermassive black hole, millions, or even billions of times the mass of the Sun. While many of these black holes remain quiet, slowly accreting matter over cosmic timescales, others erupt in brilliant outbursts, consuming gas and releasing energy that can shape the evolution of the entire galaxy. These periods of activity, known as quasars or active galactic nuclei, can drive powerful winds that expel gas from the galaxy, cutting off the fuel supply for future generations of stars. Galaxies do not exist in isolation, they are shaped by their environment, by the vast filaments of cosmic structure that stretch across billions of light-years. Spiral galaxies are often found in groups, where gravitational interactions subtly distort their shapes, pulling on their arms, drawing out streams of stars that trace their past encounters. Sometimes, these interactions trigger bursts of star formation, igniting brilliant regions of stellar birth as gas clouds are compressed by the gravitational pull of a passing galaxy. In other cases, a spiral may be stripped of its gas, left as a fading remnant, unable to sustain the birth of new stars. The fate of a spiral galaxy is written in the long, slow process of cosmic evolution. Some will continue forming stars for billions of years, maintaining their spiral structure until they eventually exhaust their supply of gas. Others will merge, their arms stretched and distorted before vanishing into the smooth, featureless form of an elliptical galaxy. In the case of the Milky Way and Andromeda, this fate is inevitable. Drawn together by gravity, the two spirals will collide, their stars thrown into chaotic orbits as they merge into a single, new galaxy. Though the process will take billions of years, it is already underway, a slow-motion transformation that will change the night sky forever. Even as spiral galaxies fade, merge, or transform, their stars and elements will persist. The oxygen in a single breath of air, the iron in the core of a planet, the carbon in all known life, each of these elements was forged in the heart of stars, scattered through space by the explosive deaths of ancient suns. The legacy of spiral galaxies is not just their luminous arms, nor their elegant rotation, but the building blocks they have provided for the next generation of cosmic structures. In the vastness of space, spiral galaxies spin on, their stars tracing patterns that have endured for billions of years. Though they will not last forever, their influence will be felt in every corner of the universe, in the stars yet to form, in the planets yet to be born, and perhaps even in life yet to arise, somewhere in the endless reaches of the cosmos. Spiral galaxies, though temporary structures in the grand timescale of the universe, have played a fundamental role in shaping the cosmos as we know it. Their luminous arms, spinning elegantly through space, are not just aesthetic marvels but engines of cosmic evolution, where stars are born, die, and seed the universe with the heavy elements necessary for planets, atmospheres, and life itself. Though their fate is sealed, whether through mergers, gradual fading, or transformation into elliptical remnants, their influence is everlasting. The materials forged in their cores will drift across interstellar space, forming new stars, new planetary systems, and potentially, new civilizations that may one day look back upon the origins of their existence and see it written in the history of spiral galaxies. Their structures may dissolve, their arms may fade, but their legacy will live on, woven into the very fabric of the universe. The light that left distant spirals billions of years ago continues to travel through the cosmos, reaching us as a glimpse into the universe's past. And as we look deeper, as we uncover the secrets hidden within their swirling arms, we are not just studying galaxies, we are tracing the story of creation itself, a story that began long before us and will continue long after the last spiral galaxy fades from the sky.